Hi, I'm Dr. Aaron Stephan, Director of Biological Research and Development at Once Incorporated by Signify. As you know, lighting can be a powerful management tool for poultry. In breeder and layer situations, especially those that involve freely moving birds, like in aviaries and floor systems, additional challenges can be faced. In this Tech Talk presentation, I'm going to outline our latest research that led to new technologies on the use of light to manage these flocks. There are four key aspects of lighting to consider for poultry. The first is schedule, or how the light changes as a function of day or the age of the flock. Schedule includes photoperiod, or the length of day for each 24-hour period. Keeping the light cycle to a 24-hour schedule allows entrainment of the bird's biological circadian clock. This clock is the bird's body's way of knowing what time of day it is or what time of year it is. The second aspect is spectrum. Light spectrum is the entire mixture of light wavelengths that together are perceived as color. The third aspect is intensity, which corresponds to how bright the light is perceived. The final aspect is distribution, meaning how the light is distributed across the floor or within a system. For breeders and layers, spectra containing red wavelengths are critical to managing reproductive physiology. In poultry, red light is perceived in two ways. The first, as you probably guessed, is by the eyes. The second way is non-visual, being sensed directly through the skull by specialized brain regions. These brain regions, called the hypothalamus and pineal gland, are responsible for perceiving photoperiod and thus setting the internal circadian clock. This, in turn, elicits the daily rhythmic production of melatonin, a hormone that regulates many biological responses. So how does melatonin influence biological responses? Well, it starts with photoperiod. The length of daylight and darkness influences the abundance of melatonin. Through a complex endocrine signaling cascade, melatonin affects the production of sexual hormones, including gonadotropin. Gonadotropin elicits sexual development in addition to secondary sexual characteristics, including breeding behavior. Additionally, melatonin enhances the immune response and counteracts immunodeficiency states resulting from acute stress, viral diseases, aging, or drug treatment. Circadian cycling of melatonin also results in anticipatory changes in fat and muscle deposition, as well as calcium mobilization and bone formation. The influence of photoperiod on reproductive state comes largely from the fact that chickens are long-day breeders. In nature, they tend to lay eggs in spring and summer when the daylight is long or lengthening. They tend to shut down reproduction and focus on growth in autumn and winter when daylight is short or decreasing. We use this fact to optimize the various stages of the bird's development. For pullets, we simulate autumn and winter by using a shortening photoperiod. This stimulates growth and suppresses premature sexual development. When transitioning to a layer or breeder house, we switch to simulating spring using a lengthening photoperiod. This process is known as photostimulation and helps to bring the birds into lay quickly and efficiently. Putting these concepts into practice, you can see here a recommended lighting schedule developed in collaboration with Highline. Here, the first phase represents the pullet stage, starting with long day to give the brooding chicks a good start, but quickly decreasing the photoperiod for rearing. Depending on the breed, photostimulation is usually done between 16 weeks and 20 weeks of age. Here, the increasing photoperiod stimulates lay. Cage-free systems pose unique challenges for bird management from the standpoint of promoting specific behaviors within the three-dimensional landscape. In an ideal system, the birds would distribute evenly throughout the system, laying eggs in nesting areas and vacating shortly thereafter. The birds would spend the majority of their time exploring, foraging, and engaging in positive social interactions. Some key lighting aspects to consider in aviary settings include that lighting should be even across the floor. Dimmer regions tend to encourage floor eggs. Likewise, under-system lighting should be brighter and uniform. Each tier should be independently dimmable. This will allow sequential illumination and dimming during dawn and dusk, thereby encouraging the birds to make full use of the perches on all tiers. Gradual dimming at dusk is critical. Before roosting for the night, the birds will often load up on additional food and water in anticipation of a longer nighttime fast. The gradual dimming lets the birds know that nighttime is approaching. It gives them the opportunity to find a perch and settle in. The simulated sunset should occur over a minimum of 30 minutes. Too fast, and the birds may become clustered too tightly in one tier, or may experience keelbone damage from missing a perch while jumping under the dim light that gives poor visual acuity. This approach also reduces floor eggs, since the majority of birds will be roosting nearby nesting areas for the subsequent morning's lay. Here's an example of how combining schedules with distribution can be useful. During the dusk time dimming process, the undersystem lighting is dimmed first. Since the levels above are brighter, the birds are attracted upward and begin moving up into the system to higher tiers. Then the in-system lighting is dimmed, drawing the birds outward toward the aisles onto their perches. Finally, ceiling lighting is dimmed to finish the transition to darkness. Lighting preference can also uncover optimal spectral compositions for managing poultry at their different life stages. Research conducted by Wageningen University in collaboration with Signify on rearing pullets demonstrated that brooding chicks prefer spectra rich in red wavelengths. As they transition from brooding to rearing, their preference switches to spectra that are more rich in blue and green wavelengths. After sexual maturation, their preference once again switches to red and rich spectra. An optimal lighting system would be able to accommodate these wavelength changes as the birds mature. In layer and breeder houses, dim red is the most preferred spectrum for egg laying. We use that to our advantage by installing cool, bright lighting under the system to encourage exploring and to suppress floor eggs. In the system, dimmer red-enriched lighting is used to promote nesting behaviors. Taking the idea one step further, understanding lighting preference gives us a new management tool for managing bird distribution in all three dimensions. We know that cluster distribution of birds leads to piling, increased mortality, and an increase in the incidence of checked eggs. As the young birds are learning the new aviary system and are developing habits, tweaking the lighting conditions to more attractive or aversive conditions can train the birds to develop a more uniform distribution. This will alleviate many of the problems associated with clustering. Sometimes conditions arise that require an immediate corrective action. One of these conditions is feather pecking. Usually initiated due to a heightened stress condition, feather pecking can quickly become catastrophic from positive feedback, whereby pecking results in visible bleeding, which promotes further pecking. Under this condition, we often advise using dimmer red light to temporarily alleviate this condition. The dim light reduces activity and aggression, and the red light eliminates visual contrast of blood and sores. Once the situation is corrected, a gradual transition back to brighter light with fuller spectrum is recommended. Another difficult period for the birds and the flock managers is during depopulation. Research shows that monochromatic blue light reduces wing flapping and locomotion. This spectrum is often used by the broiler industry in processing facilities due to its calming nature. If an aviary lighting system were capable of transitioning to a monochromatic blue spectrum, this system would drastically reduce the difficulty on depopulation for both the birds and their caretakers. Now that I've given some examples on how modulating the schedule, intensity, spectrum, and distribution of lighting can influence your flock, I'm sure you're wondering how you can achieve this level of control. To some extent, most commercial lighting options allow a limited control of schedule and intensity through the use of barn controllers and dimmers. Once's lighting portfolio is unique due to our patented dim-to-color technology that allows spectral changes as a function of dimming. Thus, the use of different fixtures for pullets and layers and different fixtures for the various locations in a system, we can achieve a certain degree of control of spectrum and lighting distribution. Over the past 2 years, our R&D department at once has had the vision to develop a fully customizable dynamic system that enables the control of all key aspects of lighting. To this end, we've developed the Nature Dynamics lighting system. This system uses a wireless Zigbee signal to control all of these aspects in an unprecedented manner. At its core is a fully independent, fully dimmable red, green, and blue channels. Each fixture can be assigned to a zone, and a wireless gateway coordinates the program from a master schedule. As the flock manager requires, the system can be tuned in any way according to the schedule, intensity, spectrum, and distribution. This system thereby represents the first fully dynamic commercial poultry lighting solution. Backed by Signify's commercial Interact cloud platform, the system will allow future firmware upgrades and recipe changes as required. Given our wealth of knowledge on lighting research in poultry, we have developed recipes that cater to various concerns faced by flock managers. These include average daily gains, feed conversion rate, daily activity and locomotion, sleeping cycle, aggressivity and pecking behaviors, activity, movement to and from preferential areas, sexual maturation and oviposition timing, piling behavior, and disease alerts. In this presentation, I've shown you specific examples of how tuning light schedule, intensity, spectrum, and distribution can benefit your layer or breeder flock in terms of production start, circadian rhythm, egg weights, egg quality, persistency of lay, and behavioral influences. I hope you can appreciate that a fully dynamic lighting system will enable an unprecedented level of control. Dynamic lighting systems like this are just the beginning. Given the large possible number of permutations, additional lighting recipes remain to be discovered. The future is looking bright.